right, so here are the answers we got. Let's go over each one just in case we're not all on the same page. So we want to take point A, and we want to do a 90-degree rotation. What I just said was that we always default to counterclockwise unless the problem specifies otherwise. So we look at G, and we want to go counterclockwise 90 degrees. What did y'all have to do first? What was your first step before you could start rotating things? You had to take 360, right? And you had to divide by the number of points on the outside, right? Because we are always assuming that they're evenly spaced, by the way. Always assuming. So how many points were there? 360 divided by 8. So we know we are traveling 45 degrees when we travel from letter to letter. Oh, you're changing your answer? Okay. So, we're starting with A. Thank you. Never mind. Not G. I'm starting with the answer. So we're starting with A. We want to go against the clock. We want to go 45 degrees and 45 degrees, which will get us 90 degrees total. So the correct answer was G. You got it right. That is the ending point for number 1. Number 2, we're going to take point H, the purple one, and we're going to go 180 degrees. Now this is the one where it doesn't matter if it's counterclockwise or clockwise. It's going to be the same destination no matter which way you go. So you could also think of 180 degrees, oh, that's a straight line. I'm going to end up at D. Or you could say 180 degrees, well, that's 45 times 4. So you could go 1, 2, 3, 4. Either way, you end up at D. Very good. Okay. Now let's do some reflecting. We want to take segment AB, and we want to reflect it over line AE. This is when you just literally picture the shape being folded, and you crease it on AE. Where would AB land? So, of course, it's going to land on AH, or HA. Ha! That's where it's going to land. All right. Last one. We're doing GH, the blue one, and we want to reflect it once again over AE. So you think about where it will fall when you flip it, and it's going to fall on BC. Are we good on that? Let's check that homework of ours. Here are the homework answers to rotations. By the way, when you see the word that says line, that's the same as reflectional. So right here, this is reflectional symmetry. Reflectional symmetry, reflectional symmetry. So those are interchangeable. Don't worry if you put reflectional instead of putting line. My first question was 3A. Name the degree of counterclockwise rotation from point X to the given point. So we are doing like literally what we just did in the warm-up. We want to make sure that we go against the clock, counterclockwise. So if we travel from X to A, the only information we need to know is how many degrees we're turning from point to point. And y'all were asking about the rotational symmetry. That's also the degrees when it's asking about angles of rotation. That's what we're doing in this problem as well. So how many points are there? 8, just like in the warm-up, right? So we know that we're traveling 45 degrees each time. So that's why 3A is 45, okay? Now everyone was asking about these at the bottom, or 4 through 6. First of all, types of symmetry. So let's start with you check every shape and you see if it has reflectional symmetry. The way you do that is you draw some lines and you see, does it look the same on this side of the line as it does on this side? And you draw another one. This is a square. It's a regular quadrilateral. We learned that if it's regular, it has the same number of lines of symmetry as it does the number of sides. So we know this has 4. We don't even need to draw it. It has 4 because it has 4 sides. So I'm going to put line, even though we know it's also called reflectional. And there's 4. 1, 2, 3, 4. Okay. Angles of rotation. So does it have rotational symmetry? I want you to picture the shape, and I want you to turn it. When you turn it, does the shape land on top of itself? Is it congruent to how you started, except for the letters? You know what I mean? The orientation. Orientation is actually the same. But so if I rotate this 90 degrees, my shape is going to look the same as how it started. That means it has rotational symmetry. So it's got line, it's got rotational. How many degrees can I rotate it and the shape looks the same as how it started? I can rotate it 90, it'll still look like that same square. I can rotate it 180, it'll still look like the original figure, and I can of course rotate it 270. How come I don't list 360, which would be the next one? Well, 360 doesn't count because all shapes you can rotate at 360 degrees and end up how it started. Okay, so let's do number 5. Number 5 is also a regular polygon. That's a pentagon. How do I know it's regular? All sides have tick marks, all angles have arcs. So I already know definitely has line symmetry, and I know how many it has. It's a pentagon, so it has 5. I'm not even going to draw them. Okay, now rotational symmetry. Since it's regular, if I take that thing and I rotate it, it's going to land where it started. I don't know if I'm describing that very well. And how do I know how many degrees it rotates each time? I take 360 and I divide it by the number of vertices, 5. And so that's how I know where it lands each time, how many degrees you rotate each time rather. So 360 divided by 5 is 72. That's when I go from here to here. What about when I rotate from here to here? Well, I just take 72 and I double it. And then I take 72 and I triple it. You get the idea? And you keep doing that. Keep doing that until you get to 360 and you know you're done. Okay? Last one. Number 6. This figure doesn't have any symmetry. The reason is I could try to draw all sorts of lines. Just play with it. Is it equal on the left as it is on the right? Is it a mirrored image? No. Do this one. Is it a mirror image? No. Try this one. Mirror image? No. Also, picture rotating it. If T went to W's spot, would the figure look the same? It would look different. If T went to V's spot, would it look the same? No. You cannot turn this except for 360, and it wouldn't map to itself. Okay? All right. Next one. Number 8. How many degrees would you rotate to get from vertex to vertex in a nonagon? Who had to Google nonagon? Who had to ask the internet what a nonagon was? 9-sided figure. So we are assuming it's regular, because if it's not regular, you throw this question out the window. So all you do on number 8 is 360 divided by 9, because there's 9 vertices in a nonagon. Okay? Number 12. I like this unit. It's fun. Okay, number 12. This one could show up on the quiz today. I told you to memorize your 4 rules. I just want you to memorize them. You reflect over the x, you change the y. You reflect over the y, you change the x. In this problem, if you reflect over y equals x, you do the switcheroo thing. You do Freaky Friday. They just trade places. It helps sometimes for some students to write the rule above the answer. Let's write the rule. This is on your notes page. There's the rule. YX. So now I'm just going to follow the rules. This first one says take Y and do nothing to it. Take Y and do nothing to it. The next one says comma, take X and do nothing to it. Take X and do nothing to it. So that's why the answer is 5, -3. They just trade places. All right. Last problem, 16. Point H. Rotated, we're going clockwise this time, 144 degrees. Now, how many do we rotate with each from letter to letter in this shape here? This one's different. How many do we rotate from letter to letter? Right, so there's 10 letters, right? So 360 divided by 10. So we're going 36 degrees from letter to letter. So now you say, oh, I need to go 144. So how many 36 degrees do I need to go? You can just divide it. 144 divided by 36. I need to go 4 letters. I need to go 4 of them. And I want to go the way the clock goes. 1, 2, 3, 4. The answer was B. The first part of today's lesson is old news. Totally already learned it when we did the similarity unit. A dilation. It's a transformation that can change the size of a polygon. You write this word in your notes. You write it in the fill-in-the-blank notes on that table I gave you. But leaves the shape unchanged. So those are the words that you're filling in the blank. Okay, dilations are going to produce similar figures. This is different. than Tuesday and Wednesday. When you translate something, when you slide it, the result is congruent to the original. When you reflect a shape, the result is congruent to the original. When you rotate, when you turn a shape, the result is congruent to the original. When you dilate a shape, the result is no longer congruent, it is similar. And the symbol for similar is that squiggly. So this is congruent, this is similar. The angles, of course, will remain the same because when two figures are similar, their angles are congruent. So the side lengths will change, but the angles will stay the same. Oh my. Also, old news, just a reminder, the scale factor is that number. It's a ratio, so usually a fraction. It's that number that transforms the first polygon to the second polygon, or the first figure to the second figure. We always do second over first, and that is a foolproof way to get a scale factor, second over first. Okay, moving right along. Also a reminder, don't write this down anywhere because we've already gone over this. We already went over this before the break, so don't write this down anymore. Just common sense. If your scale factor is greater than 1, your figure is going to get bigger. If your scale factor is less than 1, your figure is going to get smaller. And if your scale factor is equal to 1, it's called a congruence transformation. At least I'm not frozen on as weird of a face as I was last time. That one's only semi-weird. All right, let's remind ourselves how to get the scale factor. Scale factor is second over first. So what's the scale factor here? 5 over 10, 1/2. And then you always use common sense. Did my figure get bigger or smaller? It got smaller. So my scale factor should be less than 1, and it is. If the diameter is 8 and the scale factor is 3/2, what's the diameter of the image? So how do you use a scale factor? You always multiply. Every time you multiply. So you take the pre-image and you multiply it by 3/2. So 8 times 3/2, and the new diameter of this shape is 12. So you multiply a scale factor to get your image. Let's try one more. What is the scale factor? So you do second over first. Ooh, I like how this shows up in a dark figure. That's pretty. And the scale factor is 13 times bigger. Okay, we get the idea. Just a reminder, when you're on the coordinate plane, you can never count diagonally. So if I'm trying to get the scale factor, I'm only going to count horizontally, count this and this, or vertically, count this and this. Never count diagonally, just a reminder. Okay, we're going to do this slide because the true or false is important on this slide. Oh, we're already running out of time. Oh my gosh. Okay, what is the scale factor? So, I will go ahead and tell you. This is 9, and this is 3. So the scale factor is 9 divided by 3. Scale factor is 3. Let's do this true or false. True or false? ABC is an enlargement of A prime, B prime, C prime. False, right? It's a reduction, right? Okay, so if I switch these, if I switch places, then it would be true. But that statement had it all switched around. It was false. Okay, next one. The rule for the dilation is 3x, 3y. So that's how you write a rule for dilations. You take the scale factor, and you multiply it by x, and you multiply it by y. That's how you write the rule. So that one's true. If the scale factor was 1/2, the rule would be 1/2 x, 1/2 y. That's how you write the rule. Triangle ABC is congruent to triangle A prime, B prime, C prime. False. They are not congruent. They're similar. And last one. Segment B prime, C prime is 1/3 BC. And they switched it again, right? B prime, C prime is 3 times BC. If we switch places, it would have been true, but they got the fraction all wrong. Okay. I'm going to have to, you can do it at home. All right. This is the new stuff. All of that stuff that we just did was old. This is the only stuff that's new. When we did dilations before, the center was always at the origin. Every time the center was at the origin. Now we're going to do dilations where the center is not necessarily the origin. It's just any point. So how do you locate that point? How do you find the center of dilation? So what you're going to do is you're going to take a ruler and you're going to connect A to A prime. Pretend I'm using a straight edge. You're going to connect B to B prime. Pretend I'm using a straight edge. And you're going to connect C to C prime. Now, what you'll notice when you connect all of those corresponding vertices is what? What will you notice? All of those lines that you made, they will intersect. It's called being concurrent. They are concurrent. And where they're concurrent, where they intersect, that is the center of dilation. I'm going to call it O. All right? That's how you do it. So let me show you another example. So I would, even though one shape is inside the other, that doesn't change my method. I still connect the corresponding vertices, the vertices that go together. Oh, that's going to be a bad line. Connect. 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 I'll tell you where they were supposed to intersect. They're supposed to intersect at 2, -1. If you have your paper, I was close, not close enough. If you have your paper and you're using your ruler, that's where they're going to intersect. So when we have a coordinate plane, we can actually find the center of dilation, and we can do that by finding where the lines intersect and naming that coordinate. Now, just to be efficient here, if I did it correctly, how many lines would I actually have to draw? Would I really need to draw all 4 if I'm taking a quiz and I'm running out of time? No. If I'm doing it correctly, I should only have to draw 2 of those. Just FYI. Okay, last thing. Now it's the opposite. I give you the center of dilation, and I tell you to dilate something by a certain scale factor. You're going to start off by doing the same thing. You're going to take your ruler, and you're going to use that as a straight edge, and you are going to connect the dots. Connect the dots. Okay, so that's step 1, connecting. That was step 1 in the other 2 slides as well. Okay, it tells me I need to have a scale factor of 3. So what I'm going to do is I'm going to measure this. And if you measure that on your paper, you're going to get 2 centimeters. I want my new point, I want A prime to be triple the distance from O. So how far away from O is A prime going to be? Very good. So I'm going to start at O, and I'm going to measure 6 centimeters, and that point is going to be A prime. When you measure OB, you're going to get 3 centimeters. So what am I going to measure to find out where B goes? 9 centimeters away. Put B wherever that falls, B prime, and then you can connect them to make segment A prime, B prime. So that segment is AB dilated by a scale factor of 3 with center O. So what did we do? We connected the dots. Sounds like we're in preschool. Then we measured the distance and we multiplied by the scale factor. Okay, last one. Dilate by a scale factor of 1/2. So what do I do first? I connect the dots. I connect the dots. I connect the dots. Scale factor of 1/2. What does that mean? When I get my ruler out and I measure, what am I finding? 1/2. The midpoint, right? You're going to find the midpoint because you want it half as big. Divide by 2, midpoint. So you can use a ruler to measure, or you could actually find the midpoint of BP. You could find the actual midpoint. Let's pretend I found the real midpoints for real. And you connect them, and this would be A prime, B prime, C prime. So that's how you dilate by a scale factor that's less than 1. So you just take that value and you divide by 2 or divide by 3, whatever it asks for. Okay?